It's very hot. It needs to be up.
One line.
Okay.
No, can you turn on?
Okay, sorry.
What?
Huh?
That's fine.
Fine.
Because we can't see it.
Alright, so let's continue. You guys should have done matrix multiplication, right? High school, college?
No.
I don't remember.
So how would you do this? So you have a square matrix. Square matrix means what? Number of rows and number of columns are the same. Okay? So you want to multiply to 3 by 3. Why 3 by 3 here? 3 rows and 3 columns. Both matrices are of that size. So what we are doing is we're going to, so the product is also 3 by 3 matrix. Because we're multiplying 2 3 by 3 matrices, so the product is also 3 by 3. So 3 rows and 3 columns. So you're going to find the product row-wise. So I'm going to find the 3 entries, the first row 3 entries, 3 columns. And then the second row 3 columns, and then the third row 3 columns. So we're going to fill it row-wise. So how do you do that? Take up the first row in the first matrix, take up the first column in the second matrix, and do what? Pairwise multiplication. Multiply the 4 with 1, right? Plus that 5 with 4, plus 2 with 3. 4, 1, 5 times 4, 2 times 3. So do all these things, multiplication, addition, and the result is what? 4, 24, 30. So this is your value, 30. So if you want to fill it row-wise, take up the first row and then multiply with each column. So how do you get this entry here? Anyone? How do you get that value here? First row, second column. So as I said, it's first row, second column here. So which means take up the first row here and second column here. To get the first row, first column, we took up the first row and first column. So to get the first row, second column, take up the first row still on the first matrix and then the second column on the second matrix. First row, second column. Is that clear? You want, this is what? First row, second column, right? So you have to do first row multiplied by second column. So 4 times 0 plus 5 times 1. 4 times 0 plus 5 times 1 plus what? 2 times 2. That's going to be 9. Okay? Clear? Anyone tell how to get the first row, third column there? How do you get that particular thing, last thing, this one? First row, third column. So you have to keep the first row and multiply with the what? This column, the third column. There's no vertical is what? Vertical means column, right? And horizontal is row. But hope everyone knows that terminology, right? So not people blinking. So you want to find what first row, third column. So still you have the first row in the first matrix and third column in the second matrix. Do the pairwise multiplication. 4 times 2 plus 5 times 2 plus 2 times 2. What is that? 8 plus 10, 18, and then this is 26. Okay? So how do I get the second, this entry? What is this? Second row, first column. So how do I get that? So the wording itself says this is second row, first column, right? So row first, then column. So second row is the first matrix because it is second row, first column. So second row here, and then first column. So basically what you are doing, to fill up it row-wise, fix the row in the first matrix and just do the column-wise multiplication. So now we are filling the second row here, so we are going to fix the second row and multiply this with each of these columns. get this one, this is what? Third row, second column. So fix the third row as it is and multiply that with the second column. So filling the product matrix row-wise. So which means you fix whatever the row you want to find here, fix up that row in the first matrix, look at the column in the second matrix and just multiply it. Okay? Clear? You want to find out, say for example, you want to fill this up row-wise. So what you should do is, you want to fill the first row. You know the product matrix is going to be also 3 by 3, 3 rows, 3 columns. You want to fill up the first row, okay, and then the 3 columns out there. So what you'll do, take up the first row in the first matrix and multiply that with each of these 3 columns. So to get that first entry, you will multiply the first row with the first column. To get the second entry here, first row with the second column, and then the third entry, first row, third column. So you want to fill the product matrix row-wise, so fix the row in the first matrix and multiply each column. Similarly, to get this one, what will you do? This is what? Second row, but first column, right? Yeah, so you have to fix the second row and multiply with the first column. Second row, multiply the first column for this.
Yeah.
Second row, multiply the second column for this. Second row, multiply the third column for that. Okay? Row wise. So remember this, we'll use this later. Okay? Now we are going to analyze the time complexity. You should have done this in 118. Have you done matrix multiplication in 118?
Nope.
Yeah, no, we didn't do this.
No, we do
You
it.
did not do this?
No.
Did you write nested loop? 118 for
Yeah.
loops? So these are classical examples for nested loops. So the pseudo code is given here. So basically you have 3 loops for I equals 0 to n minus 1, j 0 to n minus 1, k 0 to n minus 1. So you see what we are doing here. To get one entry, right? To get one entry, if you have in general, or even here, how many multiplications are you trying to? To get this, right, what did I do? I fix up the first row and first column, right? That's what I'm going to do. And I say 4 times 1 plus 5 times 4 plus 2 times 3. Right? That you need to do all these things to get this particular thing. So, and this is repeated for every entry over there. Okay? And that's what basically we are doing in this innermost loop. You're multiplying the entries in the A and B matrices and keep adding that to the sum. The sum is basically the incremental values. Product of this plus product of this and so on. That's what the C of I comma j, this entry is keeping track of. So if you look at this, we are doing what? Some multiplications and additions, right? So we should know from a digital logic class which is more time consuming, multiplication or addition?
Multiplication.
Multiplication. So you can write as I say the basic operation is multiplication. Remember we are looking at basic operations. So for this algorithm, the most time consuming operation is multiplication. So now we want to analyze how many times we are doing this multiplication. Okay? Right? So for each the innermost loop, right? So the innermost loop basically runs, this is one value of k, this is another value of k, and then another value of k. So in this case you run the innermost loop 3 times for every entry. Okay? For each of those entries, for each of those iterations for k, you're doing one multiplication. Right? So the loop is very neatly structured. So what you can say is, for k equals 0 to n minus 1, we're doing one multiplication. Okay? So this basically finds us one particular entry. And what we have to do, we have to repeat that for all rows and all columns. Right? And that's what we are going to do. J equals 0 to n minus 1, this is for the columns. So if fixing the first row, which is your I index. So index I is for the row. Fixing the first row, filling up the columns. And to fill up a particular row and column, we have to do the innermost loop. Okay? Yeah? So just looking at the loop structure, you can come up with the summation. So now to solve this, what we have to do? It may look complicated, but it's very easy. Why? Because we have a 1 here. And this is from k equals 0 to n minus 1. So what formula that we studied you should apply here? So you have a constant like 1, you have to use upper limit minus lower limit plus 1. So apply that and tell me. So we'll fix the two outer summations and just first solve the inner one. So what should be the inner one? What is the upper limit? N minus 1 minus 0 then plus 1. Upper limit minus lower limit plus 1. So that's going to be the negative 1 and 1 will cancel out. So that's going to be simply what? N. So this is sigma I equals 0 to n minus 1, j equals 0 to n minus 1, n. Now this n, is it a constant or is it a variable? What is n, by the way, here? Huh? Why? Its value doesn't change. And what does it indicate here? What does n indicate in this, what we are doing here? We are doing matrix multiplication, right? So what does it n indicate? The size of the matrix. We are doing square matrix. So each matrix, in general, we can say it's an n by n matrix. Okay? So the n indicates size of the matrix, the number of rows or the number of columns. It's a square matrix, it's the same thing, rows and columns. So which means if it's a constant, what we can do? To simplify this further, now we agreed that n is a constant, what we can do to solve the summation further? Yeah, so before that, since it's a constant, we could take it outside the summation. So we can say it is n times sigma I equals 0 to n minus 1, j equals 0 to n minus 1, 1. So now it is again in our familiar form that we can solve easily. How do we solve this? Same thing, right? Whatever we did for k, do the same thing for j. Right? K wasn't the same thing, right? 0 to n minus 1, 1. So the formula is again upper limit minus lower limit plus 1. So if you do that, what will you get as the intermediate step? 0, I equals 0, n minus 1. This is n minus 1, same thing like this. N minus 1 minus 0 plus 1. And what did we get for that? When we do that, n minus 1 minus 0 plus 1, that's going to be again what? N. Right? So we have n times sigma I equals 0 to n minus 1 n. So what we can do again for the n, it's a constant. So we can take it outside, so it becomes n squared times 1. Right? Sigma 0 I equals 0 to 1. Because I take the n outside, already there's an n, so it's n squared times sigma I equals 0 to n minus 1, 1. Okay? So how do you solve this now? Again, we pick the same thing. This is same form, 0 to n minus 1, 1. So again, apply the upper limit minus lower limit plus 1 formula. What will you get? N squared times, anyone on this side? You want to come here? Somebody can come here too if you can't see from that side. Oh, there are a lot of rows here. So, this may be minus 1 minus 0 plus 1. So that will be again what? N square times n, which is n cube. So n cube is again what? Theta of n cube, right? So this is your time complexity. Okay? Clear? So even if you look at from a logical point of view, to get one entry, what we are doing like multiplying the row with column. Each row has n element and each column has n element, right? So in this case, for 3 row column, you're doing 3 multiplications, right? To get one entry. So if you have n elements in a row and n elements in a column, you're doing n pairwise multiplication. So to get each entry, you're basically doing n multiplications, right? To get each entry, you're doing n multiplications. N elements in the row and n elements in the column. Yes.
With the summation, the part says k equals 0 to n minus 1. What happens to that part?
That part is what we are solving first. So once we apply the formula, summation goes away. So the formula is, if you have summation k equals 0 to n minus 1, 1, the formula is upper limit minus lower limit plus 1. N minus 1 is the upper limit minus lower limit plus 1. So you get this by applying the summation formula. So once you apply the formula, summation, this one goes away.
Okay.
Likewise, the inner one. So if you apply now for this, the formula again, this summation goes away and you get this.
Okay.
Okay? So for each entry, we are doing n multiplications. N elements in the row and n elements in the column, doing pairwise multiplication. For each one, you do n multiplications. And how many rows and columns, or how many entries you have to fill here? You have n row and n columns, right? So basically you have n square entries to fill. Square matrix. So n elements, n square elements, right? N elements in each row and n columns, so n square elements. So to fill each of them, you do n multiplications, and there are n square such entries, so it's n times n square, n cube. That many number of multiplications. Right? So it makes sense even from that point of view. To fill one entry, you do n multiplication because you have n elements in a row and n elements in a column. So like that, you have n square such entries to fill. Like in the 3 by 3, you have 9 entries, 3 square entries. So you will do what? N times n square multiplications totally. Right? So n for each of them, n multiplications for each of them. So it will be n times n square. That's all sine cube. Okay? So everything comes from the interpretation of how this works. Right? So you have quiz on Thursday, right? So up to this thing, all the summation, everything from the beginning, all the proof, theorem, everything that we saw, the L'Hopital rule. Okay? Up to this point. Yes?
You have some of the slides on the blackboard.
I think it's on the course website. When you don't put everything, I don't put in the blackboard.
Oh, okay. Alright.
Have you put our project description?
Project 1 is out there. I put last night.
Okay.
Okay. So it seems now we can even go with the main JSU website like this, jsums.edu/ of course you have to use the CMS/NMEDHAN. So if you don't remember the IP address, you can use this, okay, HTTP of course. So if you go to this address, my website, Tacna State website, and then /CMS/this, type everything together, you will be able to go to my homepage. Okay? And then you see 323 on the right side, and anyone has any, I hope everyone has visited the website, right? Okay, so let's move on. So the next thing we are going to do is recursion. You should have done recursion in your 225 data structures. Do you know what recursion is? What is that?
One day.
Huh?
Okay, just one day.
What is recursion?
Is it a function defined in terms of itself?
Function calling itself. Okay. Did you study the overhead associated with it in architecture class?
Do what then?
Overhead means when your function calls itself, you need to store certain things in memory. Did you do that in your architecture class? Did you read what's called a stack in architecture? Memory stack?
Yes.
Yeah. So you need to, recursion involves using the memory stack to store things. I assigned one project on that, of course not from architecture point of view, but that will play a role here, chronological and complexity. Okay, we'll start with a simple example and then move on. Factorial. How will you find 5 factorial? What is 5 factorial?
5 times 3.
Hmm?
5 times 4, 4 times 3, 3 times.
It is 5 times, 4 times, 3 times, 2 times 1. That's 5 factorial. Okay? So similarly, if you want to find 10 factorial, it is 10 times, 9 times, 8 times, 7 times, so on up to 1. So what we want to find is how many multiplications we are doing to find some factorial. Okay, some f of n. So f of n means factorial of n. Okay, so here. So in general, you can say what? F of n is n factorial just based on what I wrote. I can write it as n times n minus 1 times n minus 2 times so on up to. Because if you say n is 5, 5 times 5 minus 1, 4 times 3 times 2 times 1. So n factorial can be written in general like n times n minus 1 times n minus 2 times up to 1. Which was then this is 118, right? A for loop to find n factorial of n. Did you do that? What programs you did that course?
We had Bailey.
Yeah, we have that.
That doesn't answer for my question. I asked what programs you did.
What did we do? Really easy, really simple stuff.
Yeah, Bailey didn't do much.
So this is again a classical for loop. Instead of summation, where you keep adding things, you will keep multiplying. Okay? So if you want to write a simple for loop for it, what you should do? For I equals, of course, this is pseudocode. I equals, I can write the same Java code. So I equals 1 to n I plus plus. So declare some factorial equals 1 outside and factorial equals factorial times I. As simple as that. And then you can, this is what the loop is, and then you can print out factorial. Okay? This is not recursion, this is iterative. You do go to a loop sequential. First multiply by 1, store it in factorial, and then multiply this by 2 and update the factorial value and so on. Okay? So this is iteration. What we are going to do is another way called recursion. Okay? So, just by looking at this, I say n factorial is n times n minus 1, n minus 2 up to 1. Applying this definition, can I say this term, which term? This part here, what is this? This is n minus 1 times n minus 2 up to 1. We can say that is what?
N minus 1 factorial.
Good. So this, just this one up to from here to here, or looking from the other side, 1, 2, 3 up to n minus 1 is n minus 1 factorial. So what can I say basically? N factorial is n minus 1 factorial times n. Because multiplication is commutative. A times b is same as b times a. So n factorial is n minus 1 factorial times n. Isn't it? of 5, right? Let me write it somewhere on here. Can I wipe this side? Okay? So which means if I want to find factorial of 5, what I can say, factorial of 5 is factorial of 4 times 5, the integer 5. Okay? So factorial of 5 is factorial of 4 times 5. Is that clear? Because this is basically your 4 factorial. Now same thing, I can say factorial of 4 is what?
3 times 4.
Huh?
Factorial of 3 times.
Factorial of 3 times 4, integer 4. Okay? Same way, factorial of 3 is factorial of 2 times integer 3. Factorial 2 is factorial of what? 1 times integer 2. You can go even one more step. Factorial of 1 is what? It's 1, but we can go really to the basic condition. Factorial of 0 times 1. Anyone knows what is factorial of 0? What is 0 factorial?
1.
Good. 0 factorial is 1. So we go all the way to the basic condition. Either f of 0, f of 1 depending on the problem. In this case, we can go all the way to 0. And that is well defined because we know we can say f of 0 is 1. Alright? So to find f of 5, we are not going to do like the iterative procedure. We are going to go to a lower value, say f of 4, and find what f of 4 is. And multiply whatever is f of 4 by 5. F of 4 times 5. So which means we need to find f of 4, factorial of 4, and that is f of 3 times 4. And f of 3 is f of 2 times 3 and so on. So we go all the way down to this. And now what we can do, we can substitute back, which means now that we know f of 0 is 1, I can substitute for f of 0 as 1 and say f of 1 is 1 times 1, which is what? 1. So I found now f of 1, factorial of 1. So then what I can do, I can substitute for factorial of 1 here and say 1 times 2 is 2. And I can substitute for f of 2 here, the 2 value 2, and 2 times 3 is 6. Then I can substitute f of 3 here, this 6. 6 times 4 is 24. And then we have f of 4 is 24. 24 times 5 is 120. Right? So where does the stack thing that I told you before comes here? If we want to find f of 5, you are calling the function f of factorial of 5 once, some factorial, right? Function, and you're passing 5 as the argument to that function. And what that internally does, it calls factorial of 4 to find factorial of 4. To find factorial of 4, you have to call factorial of 3, and so on. So all these things have to be, like I laid out here, they have to be stored in the stack. Because these are all active function calls. Because you call f of 4 to find f of 5, then you call f of 3 to find f of 4, and so on. You go all the way down here. And then you go back and solve